1 minute. Just
Rubaiyat Tanbir Hussain, Chattogram University of Engineering and Technology, Chuet, Bangladesh. If I may, I would want to give a gentle reminder of some basic rules to ensure an uninterrupted session. During the speech, all other participants will have to mute their microphone. If the participants have any question regarding the ongoing speech, all are requested to submit their question in the Q&A box section, and live Q&A section will be conducted by session chair at the end of this session. Now, I would like to request Professor Dr. Muhammad Rubaiyat Tanbir Hussain sir to lead this session. Sir.
Thank you, Mr. Rafiul Islam. It is my honor to get the invitation as a session chair for these important topics on power electronics. First, the field of power electronics is very important and interesting. You know that amid the rapidly changing innovation landscape, the field of power electronics has experienced a large growth and sustainable technology for the beginning of fourth industrial revolution. The expanded market demand for power electronics has been due to its vast application in autonomous electrical vehicles, including drones, artificial intelligence, robotics, 3D printing, etc. So I feel it would be a nice informative session to know the opportunities we have and the challenges we have to face in the coming future in the field of power electronics. So first of all, I would like to introduce our keynote speaker, Dr. Ofik Bhattacharya, and I would like to present his short biography, which has been displayed here. We all have seen this here. Dr. Ofik Bhattacharya is working as an assistant professor in the Department of Electrical and Electronic Engineering of IIT Roorkee from February 2014. He completed his BTech from Sikkim Manipal Institute of Technology in 2002 and MTech and PhD from IIT Kharagpur in 2005 and 2010 respectively. He became student member and senior member of IEEE in 2006, 2013 and 2018 respectively. Prior to joining IIT Roorkee, he has worked for R&D division of solar semiconductor and Samtel Avionics during his short stay in industry. He filed 2 international patents on solar pump and power quality. At present, Dr. Ofik owns 2 international patents and 1 national patent. He has also published 15 SCI index journals and 30 conference papers. Among the 15 SCI index journals, 10 among them in IEEE or IIT. He is also principal investigator of 3 research projects supported by DST, SCRB, CSIR, CPRI, and 2 industrial projects supported by companies like Statcon, Energia, and Tata Power. He has also authored, as he has already guided 2 PhD students and more than 15 MTech students. He has also offered 4 NAPTEL video courses and conducted 2 short-term courses in QIP as principal investigator and collaborator of Xeon courses with foreign faculty. His field of interest is power converter topology, electric vehicle, microgrid, power quality, converters for renewable energy. Now, I would like to request our distinguished keynote speaker to kindly start your session.
Thank you, Professor Hussain, for your introduction. I take privilege to talk about the recent advancement mainly in the power scope and futures future power electronic opportunity and challenges. So my slides are visible?
Yeah.
Okay, fine. So the it is changing, right? The second slide has come?
No, sir,
No.
your slide is not visible.
Just a minute. Give me a second.
Okay, sir.
So I should share screen. Okay, share. It is coming right now.
Yes, sir, it is now visible.
Okay, so it's changing.
Yeah.
Yes, sir.
Okay, thank you so much. Okay, thanks for a nice introduction. Okay, so I'm honored and privileged to talk about the scope of the power electronics and the challenges. So ultimately, if we Indian mythology, you know, knowledge is considered to be a trade, bodhimix. So, you know, if you consider the same connotation here in power electronics, so consider it as a tree. So it has a roots and it has a branches. So it has a root. So it takes inputs from the physics, maths, circuit theory, analog electronics. There are power-based system, control system, and we require to the computer-aided designs. These are the input to the power electronics, and ultimately we produce the product, and thus we have a branches, and thus we can have a electric vehicle, motor drive. You know, power quality is some problem mostly arises due to the power electronics, but we also seek the solution by the power electronics also. It is something like vaccination. So as well as the renewable energy sources. So broadly, so we have an immense scope of the power electronics, and to know the power electronics better, one has to know those entity quite well, that is physics, math, circuits, power system control, and the computer-aided design. So then only we can, I mean to say programming. So then only we can understand the power electronics better. So now, what does power electronics do? Ultimately, if you talk about the drives, we know that heart of the drive system, electric drive system, is the machine, but it has to fit with the proper voltage as well as control. Thus, it gives the efficient, flexible control and the conversion. And another aspect is that it typically involves control and the change of voltage and current, because as we know that, you know, in a drive system, for the asynchronous machines or the induction machine, if you run at close to this, its synchronous speed at a particular frequency. So frequency conversion is required, voltage conversion is required. And furthermore, conversion in efficiencies are quite high. So if you convert AC to DC, DC to AC, so you expect that conversion efficiency will be 90%. Whereas in a thermal system, you can see the efficiencies are quite low. So thus, we talk about sustainability. That is, whatever the energy, we can leave it to the next generations. Then environmental footprint, whether we are reducing the carbon footprint or not, energy efficiency, availability, or the next modern system of living, it is affordable to the human being or not, and the quality of life. It all can be addressed and focused by this power electronics with the help of power. Now, journey of power electronics is quite long. Of course, now by means of the power electronics, we understand the solid state devices. But solid state devices comes into the picture when BJT was invented. Before that, there was no solid state devices. So, but prior to that, we have a mercury arc vacuum rectifier. You know, Calcutta Electric Supply Corporation used to have, I have seen personally, even in 100 years later also, in 2001, that Marconi arc rectifier has been operating, and they kept it in one of the substation for the training purpose. So Marconi arc rectifier started its journey in 1990, but it was a thermonic emission kind of entities, and its efficiency was quite low. I think in 1945 or 46, BJT was invented. And after a decade later, there's the invention of the thyristor. So from the invention of the thyristors, era of the power electronics began. And the power thyristors, thereafter we produced that, this is a half control device though, and the first phases was 1957 to mid of the 1970s. So there we got a power diode and the power thyristors, etc., etc. And thereafter, after 70s, this is the first, we say first generation of the power electronics. Pardon me. Sorry. Extremely sorry. We have our next generation power electronics. So that is the full control devices. And full control devices, mostly those in 1957 to 70, control was mainly in the analog domain. Then the full control devices came, that is GTO, GTR, power MOSFETs, and these are digitally controlled. So we got a 8085, 86, those domain was entered. And thereafter, after 80s, Professor Bali invented the IGBT. Now, and the power MOSFET and thyristors, all were also this switching frequency changes. Instead of the microprocessor, we have a more complex DSP-based processors or the FPGA-based processor. Even after I have stopped here, we have now 4th generation devices, that is a high band gap devices, and also the FPGA. So this is the journey of power electronics, still continues. Now, what are the challenge? Challenge definitely is that power densities. So we require to address this challenge quite heavily, because we require to see that there is a power dissipation. Ultimately, there is a requirement of the heat sink. So heat sink size will be more if there is a more power dissipation. If it can be reduced, then it will be more compact. And thereafter, high reliability in extreme environmental conditions. We design our product, and it may be used in sub-Saharan Africa, or it will be used in Siberia. So in extreme weather conditions. And so we should be prepared to design to take the limit of tolerance. Thereafter, lower magnetic emission, because nowadays, we have a lot of communication devices. We are talking about 4G. We are using the Google speaker. We are using Alexa. All are the communication devices. We have a home automations. And if our power electronics devices interact with those devices, then it may malfunction. So for this reason, we have to suppress the conducted and the emitted noise or the emission. And thereafter, we as a user will be happy to see a turnkey system. You give in a boxes, a plug in, it works. That's all. We as a user doesn't bother to know the integrity and the nitty-gritty of it. Thereafter, high level of integrations, and we see this is basically the can we make this ASICs with VLSI and other aspects, and lower through life cost. So what is the operating cost of it? So we got an operating cost for this is now India, we have a petrol prices is very high now. We are all debating to have the electric vehicle right now. So electric vehicle, if we charge to solar, It is extremely economic. So for this reason, we are talking about what is the life cost of the ownership of this car, let's say. Now the motivations. Product driver led. Of course, we got a emerging critical applications. I won't say no longer it is emerging. Wind power is harvested quite well. We in the western part in India, there is a plenty of it. We call it the wind mines. So we try to contribute around 10% of our demand from the wind. That is our target in 2025. So that is in considering that India is a huge country, is a huge demand. There is solar, and solar, we have an extremely high reliability now in solar, and and now we are facing another challenge because of the huge production of the solar. Now solar tariff, we are talking about 10 years ago, the grid parity, how much the solar price energy will cost and how much the grid energy will cost. Now solar tariff by the reverse bidding available in India in 2 rupees 30 paise, whereas we are purchasing the grid power at 6 rupees almost, depending on the different kind of tariff or the domestic issues. So having a reliability in power electronics, that is, but the challenges is there. Let's say we got a solar eclipse. If you have over dependency on the solar, then what will happen? Same way avionics, critical applications, and the harsh environment. So how you can minimize those harsh environment and critical issues, and we can keep the reliability. And thus, we require to have a paradigm shift in research, and we require to have the contingency designs and handbook of the calculation and testing that have physics of the failure approach design reliability, and thus you come to the more reliable and the cost-effective power electronic systems or the fault-tolerant system. Now we talk about the future scope in detail. This is a projections 5 years ago. So whatever the devices, silicon-based devices we have, and we can throw the power just 10 to the power 3 times more. So we have the silicon IGBTs, that is the low-end solutions. Then we got a super junction MOSFETs, and they are silicon-based IGBTs that is coming out to be the 200-volt solution, but switching frequency has to be low. But once you are going to the y-axis, we can also increase the switching frequency. You can see that for this decisive-based devices will have the higher switching frequency as well as the higher power rating. As you understand that you can increase the switching frequency, then let's say having a V/F control. Same machines, instead of running at 50 hertz, if you run at 1000 hertz by the V/F control, you can override the motor state away at 20 times. So thus, what happened? But that's not that easy, we have other challenges. So just the same machines, which is 1 kilowatt, can be overloaded to 20 kilowatt. So this is the scope of the power electronics in brief. Now, the basic application of the power electronics, and many of you may be actually in front of the power electronics, considering that you have students, they are the futures of us. So I have kept this slide because let us have briefly talk about few introductory things also, entities also. The high frequency power electronics is essentially a DC to DC converters and inverters. And thereafter, these are both are very frequently users, because DC to DC converter finds its application in the solar photovoltaic cells, to track the MPPT and to maintain the DC link voltage. And thereafter, we may actually having AC systems and have inverters. And low frequency, gradually we are now phasing out, but still we are using, it is line rectifier, and you can have a distributed power system, that is power devices. And now, since I can cite an example of India, for past 20-30 years, load center of India is in south. So you might have heard about the Bangalore, Hyderabad. Those cities actually are picking up the most of the entrepreneurial activity, and thus the load shifted there. But coal is available in the eastern part of India, that is Bihar, West Bengal, Jharkhand, all those places. And if you want to have a fossil fuel-based transmissions, it is better to put the coal-fired station where the coal is available. So thus it will be in eastern region. Unfortunately, due to some reasons, economy didn't pick up, and thus it is seen that instead of putting a thermal power station there, it is better and easy to transmit the powers from that place around 800 kilometers, 900 kilometers from the place of origin of the coal to the load center. And it can be HVDC, it can be HVAC, or it can EHVDC also, extra high voltage AC or DC transmissions. And there also the power, that can be helped with the aids of the power electronics. Then the power quality. Of course, many of us blame power quality is for the power electronics only. But that's not totally true. We are using the arc furnace, based welding and all those things before of the power electronics comes into the picture, or power electronics in infancy. So now it has been, of course, it has been highly aggravated because of the power electronics devices and of the mostly this active power, mostly this adjustable speed drive and AC to DC conversion. Thereafter, we got a front-end inverter. And thus, we can do the passive filtering. Instead of that, we are looking for active filtering, but we can mitigate the problem of the power quality. Now, thereafter, control. One aspect that, these devices has to be controlled, and it has to be properly monitored to keep the desired output. And for this reason, power electronics takes a lot of input with the modern control system. So one power electronics design engineer has to be very good also into the control system. So let us talk about now next step, the voltage and current rating of the major switching devices which is commercially available. Now you can see that I have seen a slide previously that GAN devices, these are practically available. In x-axis is the current scale and y-axis is the voltage scale. So you can see that SCS can handle a very high voltage, and IGBT can have you can see that brown color how it changes. If you want to have a very high current, then its voltage rating is little low, and you have to be a compromise between the voltage rating and the current rating, and it is almost a constant power devices. And I'll show a little later that switching frequency. Switching frequency of the SCR is the smallest, and there it is like the semi-controlled devices also, but power rating can be into the MVA level. And thereafter comes to the GT or the GCT, so that can handle power, and it's the middleman in the row up to 6 kV, but the power rating is power rating is generally 1,000 times or 100 times less than the SCS. And of course, you have a fantastic control devices, that is IGBT, where we can go to the switching frequency close to the 100, close to the maybe 10 kilowatts or some range. But there you can see that it is not possible to build any system more than 100 kilowatt or 100 kVA. So this is the challenge. So for this reason, we want to have a IGBT, and that devices we want that can be operated in the range of the 100 of the kilohertz. And if we can do that, then it becomes very compact. The electronic switches characteristics by these are the few aspects we require to keep it in detail about it. So that is the while of course while analyzing we consider the switch is ideal, but practically not so. So we have to see that parasitic into the account, and we require to see that once this commutation takes place, that when one switch is off and another switch is on, then how the spikes, notches, and all those aspects taken place, how we can suppress actively. So, and these are the something what we assume these are all ideal, but there is a huge deviation when we actually design a practical power circuits with the help of the power electronics. For this example, I just take a brief example. You have studied a lot because it is a power diode. There is one difference of the power diode with the normal diode, because there is an extra in positive layer to increase its blocking voltage, and that it is a 1/4 devices, and this is how it will work. Thereafter, thyristors. Thyristors in a semi-control devices, and same way thyristors has a big set of numbers. Mainly we talk about silicon control thyristor is a prime member of this member of this category. So we talk about that only first. Thereafter, GTO we can have a get turned on and turn off, and thus it can be a full control devices. Now, transistors has seen a lowest life cycles as a power electronic devices with the invention of the IGBT. So, benefit of the MOSFETs and the benefit of the BJTs have been combined by Professor Bali in G, and thus we got a excellent device called insulated gate bipolar transistors. And then power electronics got a huge flip once we got a IGBT devices. Now let us come to please recall our slide few minutes ago. That is, these are called high bandgap devices. You can see, there is a capacitor between gate and source. We call it CGS, and same way CDS. Instead of that, and generally silicon has a low band gap, but these devices will have the higher band gap, and GN transistor will adopted with a wide range of applications, and it can handle huge larger switching frequency or the fast switching frequency, but there is a configuration you can see that you have to take out the trapped charges. So pin 2 you are giving maybe the positive pulses, and pin 6 you can give the negative pulses. So we draw it faster. Same way you can actually also bias the source also with the supply, so that make this band gap higher, so that for a faster device, or to take out the current trail. In IGBT you might be aware of that there is a current trail. Once this current trail stops, then only it will go to the full blocking stage. To reduce the current trailing, all this arrangement has been given. I don't have a scope to discuss in detail, but you are free to write to me, I'll discuss in detail. Now see that, what are the challenges of the high switching frequency of the normal devices? That is DVDT. And you got a capacitor, and thus you got a CDVDT. This is nothing but a current. Ultimately, that driver has to sink that current, and it is about the gate to drain capacitor, and you also have a CGS, and you have a stray inductance. You may not have physically connected the inductance, but inductance will come because of the stray inductance of this board, of the wire, and thus we require to design it properly. Once these are the really challenges, once you are going to the higher switching frequencies, Even the lead of the capacitor will behave as a inductor. So those are the many issues while have to be considered while practical designing. So for this reason, we require to avoid few things. So low LG to avoid ringing. We require to have a negative gate bias to -2 to 3 voltage. This is recommended. So these are the few aspects which become extremely challenging when we go for the high frequency operations. But there's a huge benefit if you can do the proper design. We definitely will reduce the size, cost, everything, and make it a product more compact. So let us talk about what we know very well are the 6-bus converter we are using from the first generation of the power electronics, that is in 1970. So still it is using, it is using in 8-bit DC system, where this has been put into the cascade manner to handle the huge voltages. But there is a problem of the power quality, because as you know that, it throws the harmonics. It is a 6n plus minus 1 will be the harmonic into the system. It throws the harmonics into the source. And thus we seek a multi-pulse converter. And it is called a 12-pulse converter, and it is physically available here. What happened, we are using the power system of vector group. So start delta conversion, we need not have to do a special requirement for make a special kind of transformer to do that. But if you are going for the other pulse converter, then phase shifted become different. 24 pulse converter, let's say, when you are a 15-degree phase shifted, a special purpose transformer is required. So anyway, and in that way, we can also actually reduces the harmonic component into the supply side. There is a power quality problem. And in a megawatt level power handling of the machines, this is one of the suitable solutions. Go for the 18 pulse, 12 pulse, etc. And where you can reduce the considerable amount of the problem of the power quality. Now let us consider the multi-level inverter. We are living in the age of the inverter now. Essentially, now we say that AC, I mean air conditioning, inverter fed ACs. So what essentially is do that, it rectifies it. So while rectification also, it should not inject any harmonics. And thereafter, we want to feed a sinusoidal waveform. Instead of that, we got a pulse rippled pulse TC rather. So we require to be it is a square wave, and we can see that the power quality is a 46%. And now for this reason, we go for the multi-level inverter, where we can use the number of levels, where you got a 0 plus VDC and a minus VDC, and same way you can have a multiple level, and it looks like a staircase, and it is more close to the sine wave. So this has been realized by the mechanical switches, and ultimately it looks like close to the sine wave. Thus, what we can reduce. We have reduced the DVDT, because if you have a square wave, there is a high DVDT, and there is a capacitance between the ground and any bodies. So there will be a huge body current of the capacitor, and there will be unnecessary losses, and insulation will damage after a few years. We have to de-rated on the capacitors because of the harmonic presence. All those can be tackled by the multi-level inverter. So in brief, what we can say is that, so it improves the power quality. Why? Because we have suppresses the number of harmonics, and good harmonic profile, and the requirement of the filters is reduced. If you use the square wave, then we have to put the filters. Ultimately, filter is taking the buck of the problem of the harmonics, and thus the lifetime of the filter will be less. Ultimately, we require to replace after a few years. So therefore, then thus it leads to the lower DVDT and the losses. And flexibility of the control, we know that there is a lot of modern control system in the machine drive. This is the vector control or the field-oriented control. Thereafter, direct torque control. These can be made available with those flexibility. Now, let us talk about the inverter based on the topologies. So we have we want that few features, as I talked about, that existence of the multiple redundant states, so that whatever the voltage we require to generate, we can generate even if some switches are non-operative. And the fault tolerant is possible, and equal load sharing among all the switches in a healthy condition, so that the heating is uniformly distributed and there is no localizing heating, and so there is no local hotspot. And easy to integration with the renewable energy sources, it may be one of the intention of it. So for this reason, I just talk about a little bit of the multi-level inverter. Multi-level inverter can be single sourced or the multiple source. There are diode clamp and the cascade and the flying capacitor. These takes only the single source, whereas the multiple DC sources having a cascade H bridge and the asymmetrical one, and where you can increase the level by the bricks. You add up the bricks and you get the level. An asymmetrical multi-level inverter cascade H bridge with a smaller amount of bricks, you can achieve 22 level, 27 level, huge level with that, and thus it will be more staircase, and thus you got a less harmonic problem. Now, of course, as I told you, the conventional inverters are the diode clamp inverter, the capacitor clamp inverter, and you see that this is the diode clamp inverters, and there is a logic, but one of the problem is that it is a 3-level inverter. For M level, M can be any, it can be 10 also. So you can see that. So how many diodes are requiring per phase? This is only one phase circuits. You talk about a 3-phase, so it will be multiply the component, and we got a huge component count, and thus it is no longer are the compact solutions. But of course, the advantage is a high efficiency. No need for the filter size is reduced, and the reactive power flow can control, because when one of the problem is that when you have a RL kind of load, mostly in the induction machines, so voltage may be positive, but current may be the negative. So that devices require to path of the current to flow, and that path, if it is absent, so that topology cannot be realized. So for this reason, we have to see those entity, but it fulfills that entity. However, the disadvantage of it that number of huge component counts, one of the major disadvantage, and high voltage rating of this blocking diodes, and unequal device rating, and the capacitor unbalance may be another problem. We may be actively required to balance that capacitor. Same way, we got a flying capacitor. Here, instead of a diode, we got a capacitor, but there were the 2 diodes. You can see that there is only one diode. So ultimately, I cannot go to the nitty-gritty of the operation for the shorter time durations. But what is the advantage of these devices is that the number of diode was M1 minus M1 into M2. Here it is divided by 2. So number of capacitor is less here, and ultimately you have a less component count. But and it has a lot of redundancies. You can generate a particular phase with a particular switching combination if particular switch is off. So for this reason, for increasing reliability, we consider the multi-level inverter with a flying capacitor. But one of the disadvantages of the multi-level capacitor is that capacitor lifespan can be very low considering the device. So this is a challenge we require to address, and that redundancy also required to be vacuum. And this is the example of the cascade multi-level inverter. And it is you can get those voltages add up, and ultimately you can scale it to the any level. Here it is a symmetrical multi-level inverter. Logic is very simple. You got 2n plus 1. If there is a 4 bridge, you get simply the 9 level. But of course, with the asymmetrical, you can get a huge number of levels with asymmetrical switching. But one of the disadvantage of this is that we require the isolated DC sources, but this itself become an advantage for the solar panel, we can have isolated solar panel as isolated DC source, and there you can feed it to it, and thus we can get those levels very easily. Now, I just show you a little bit of examples of the asymmetrical. We can have the asymmetrical, that is B1, B2 in the progressions, and we can get a different kind of voltage level. And one of the challenge is that advantage of the asymmetrical is that we can increase the higher level of voltage, but problem lies that, you know, control logic is complex and switching redundancy is compromised, because, you know, if some switches goes away, so you cannot achieve that. And renewable energy integration and the management with the MPPT is also been a challenge in a partially setting conditions and other. So now I just talk about this brief, then I should pause, I think, you know, and actually we have a QA sessions after that, right? So we can continue till what time?
Sir, hello, sir.
Yes, I can continue till what time? Because
the time schedule was from 2 p.m. to 3 p.m. with question and answer
there's a
section.
QS, right? So
yes, sir. So
you tell me when I should stop, because
okay.
I can. Okay. Huh?
Okay, sir. No problem, sir. I will.
So when we can start the QS? Okay.
Okay, sir.
So now another aspect, another motivation in how whether we can reduce the number of switches. Fine, we address the redundancy. So we now, of course, if we reduce the cost of the component, that will be a huge benefit. So for this reason, we are looking to the reduced switch multi-level inverter. So another consideration of the considering that reduced switch topology is the total number of POS switches. And while doing that, whether using the rating of the switches or not, and that is the blocking capability of the voltages and the current carrying capability of those devices, and optimal controllability, whether suffered or not, because that system has to be controllable as well as observable. Because otherwise, for example, in a midpoint of Western base, it is not controllable. So we should not have those kind of entities. So for considering that, we'll go for the inverter with the reduced switching topologies. So these are the few parameters directly affecting those devices. This is one of the examples. You can see that, you know, we can achieve, this is a reduced switch topology, and we can achieve huge level with that. It can achieve around, if it is asymmetric switching, we can achieve 21 level with that, even 29 level, depending on the kind of switching logic you want. But what we require to check here, whether it has the reactive power feeding capability, and whether the stress across the switches is more or less. So these are the few entities that have to be observed, and that has to be okayed. And what about redundancy? But generally redundancy has been compromised here. If one switches is lost, you cannot achieve that same level, but that doesn't matter if you are not getting a 29 level, instead of that you are getting a 22 level. That should be actually suffice your requirement of the THD prescribed by your grid. So this is another format, you know. So you can see that, and one of the advantage of that, you know, you are showing as a battery, it can be replaced by the solar panel, because then these are available to you, and thus we can have a huge number of level possible. So this is the few examples of the hybrid multi-level topologies where you can cascade. You see that what you did, you cascade the first one, you cascade this diode clamp with the cascade multi-level inverter. So this is a 3-level multi-level inverter followed by a cascade multi-level inverter. That number of sources got reduced, and in that way, you can optimize the sources and the devices. And that optimality is also been a focus area of research nowadays, so that we get the optimal topology. And yes, so I should stop here.
For 10 minutes actually,
yes.
Including the question answer session. And if you could go a little bit faster.
Acha, by the way, can someone read out the question? If they're asking, I don't find any questions.
Okay.
Sir, if you are getting a question, please read me for me.
After completion of this session of your talk, we will ask the audience to have question answer or discussion.
So fine, then actually I stop here because my presentation, now you can start the QS, we can answer based on.
Yes, sir. Thank you very much for your nice presentation. So now the floor is open for the Q&A. I am drawing the attention of attendees. If you guys have a question, Dr. Ovik Bhattacharya is available for your answer. Please.
Okay. One of the audience asked a question to Dr. Bhattacharya: why frequency can be reduced in parallel inverter?
Why?
Why frequency can be reduced in parallel inverter?
Parallel inverters. Okay, parallel inverters, it is mostly operated. Let's say we have a 2 solar inverter injecting to the grid. So we have to go to the basic principal operations of the connecting to alternator in parallel mode. But what happened, so there is a doping characteristics and all, we have to see that. But what happened, that THT contaminations will differ with the, because you please understand that once you have the inverter, you are not injecting a sinusoidal waveform. Essentially, you are injecting a square waveform and it may be the filtered, and that gives you the delay. So for this reasons, we have to see the harmonic contaminations of both the parameters, both these inverters, and ultimately which one is the lowest. Which one is the lowest? So this one will become the pilot, and ultimately we ask to sync the other inverter to be with that. And then what happened to do that? Maybe the switching frequency has to be compromised for the higher switching devices, but to meet the requirement of the 2 inverter working parallel. So what operation of the parallel inverter itself is a very challenging job with a non-known circulating current, while equal phase shift for the different inverter, because you are putting definitely a filter. So there, what is the control strategy? You can do it. You can play only with the modulating wave. So you can only play with the switching frequency. The switching frequency can be changed to adjust, and not always, it is lower. It is possible to make it higher also. There is also a research area. So ultimately, we require to match those 2 characteristics, and thus, while bridging, we require to manipulate the harmonics, and that is basically manipulated by the help of the switching frequencies, and thus we require to be sometime when we change, most of cases, it required to be lower the switching frequency for operating in a parallel manner.
Okay, Dr. Mohammad Rubaiyat Tanvir Hussain sir, as we have no questions in our chat box and Q&A session, could we end the Q&A session here?
I just request, I have given my email ID at the beginning. So
yes, sir.
You can note it down, the participant can note down. And if you have any queries, please write to me. I'll be extremely delighted to answer your queries.
Okay, sir. Thank you. It's Your Highness. Now it's the end of the Q&A session. I would like to request our session chair, Professor Dr. Mohammad Rubaiyat Tanvir Hussain sir, to hand over the virtual certificate to our keynote speaker, Dr. Ovik Bhattacharya sir, as a token of appreciation.
I am honored and humbled.
Yeah.
Thank you very much, sir.
Have you with us in this session for your nice and informative presentation on power electronics, the opportunities and challenges we have in the future. Thank you. Thank you very much.
Okay.
Thank you, sir.
Thanks.
Now, I would like to request one of our honorary chair of the conference, Mr. Fuad Ahmed, Senior Lecturer, Natural Science Department, to hand over the virtual certificate to our session chair, Professor Dr. Mohammad Rubaiyat Tanvir Hussain, sir.
Dear Professor Dr. Mohammad Rubaiyat Tanvir Hussain, sir, it is my immense pleasure to deliver the e-certificate to you. I would kindly request you to accept the token of appreciation for your immense contribution in this conference. Please, sir, accept the token of appreciation.
Thank you. Thank you very much. I feel honored to be here as a session chair to conduct the keynote session. And I thank you very much, all of you, and hope that the conference will be very much informative to the students and all the faculty members of the Kochi University and all the participants. Thank you. Thank you all.
Now, I would like to request all of you to open your camera if you are comfortable enough so that we can capture this moment. Thank you, sir.
Hope that we will come out the non-pandemic days and we'll meet physically and have a physical picture soon.
Now we have reached to the end of the session. Thank you very much, Professor Dr. Mohammad Rubaiyat Tanvir Hussain, sir, for conducting this keynote session. I also thank our keynote speaker, Dr. Ovik Bhattacharya, sir, for managing some time for us and also for your nice presentation. I hope it will be highly motivating and beneficial for all of us. Thank you all. Have a good day. Thank you very much, sir, once again.
Thank you. I'm logging off.
Thank
you for your chat.
Thank you very much.
Thank you.